part of the screen.
I thought I clicked already. There it goes. I don't know why it didn't move.
All
Right, so now we're going to be solving in this podcast solids of revolution using the washer method. So solid of revolution is a solid that's generated by revolving a plane region around a line that lies in the same plane as the region. The line that we're revolving around is the axis of revolution. So here we have some familiar solids. All right, so here we're revolving. If you revolve a rectangle around a line of revolution, you get a cylinder. If you revolve a semicircle, you get a sphere. If you revolve a triangle, you get a cone. And if you revolve a rectangle, and the rectangle isn't touching the line of revolution, you get a cylinder with a hole in it. I don't know what to call that thing.
Tube?
Tube. We'll call it a tube. Sounds good.
So you're just revolving the line and not the actual shape?
No, you're revolving the figure around the line.
Yeah.
Wait, can you go back a slide then?
Yeah.
I don't care about
Come on,
those
Russell,
people.
pay attention.
So that triangle right there, if you revolve it, why would there be a hole in it?
There isn't.
There isn't.
There isn't around these. These are just solids of revolution.
Oh, okay.
Yeah.
Yeah, it's a solid. It just looks like it's got a hole in it.
All right, so now we're going to look at the washer method. So a solid of revolution, for the washer method, our cross section has a hole in it. Right, so, and that's why it's called the washer method, because it looks like a washer. So the area of the surface of a single washer is just the area of the outer circle, minus the area of the smaller inner circle. Okay, so it's going to be the big O, big O, circle O? I don't know what the heck I was writing there. But it's going to be the big circle minus the little circle. All right, so find the area of a circle. That would be pi r squared, right? And so the big pi r squared with the big R, capital R there, stands for the larger circle. The lowercase r stands for the smaller circle, and they're both multiplied by pi. So usually we pull the pi out, and then we just have r squared, big R squared minus little r squared, where each of those is the radius of a circle. Okay? So the volume of a single washer is just pi and then times the large radius squared minus the small radius squared, because it's the big circle minus the little circle. And then we integrate a dx. If we integrate those, so if we integrate, then we're adding all of them up from A to B, then we get the volume of all the washers. So this would be the single washer, and then integrate, we get all of the washers, and we get the volume of the solid. Okay? So the volume is just going to be from the integral from A to B. We'll have the pi, which we can pull out in front, and we're going to have radius squared. So the radius is the outer function minus the inner function, so the radius of the inner function. So it's large circle minus small circle, and then times pi, of course, because these are circles. Okay? So pull the pi out, and so our formula is going to be pi times the integral from A to B, f of x squared minus g of x squared, where f of x is the outer circle, outer function, and g of x is the inner function. Right? And actually, let me go back to my diagram there. So you can see that there in my diagram. So f of x is that outer line right here. Right, so as it rotates around, ignore the inside, we get this, we'd have this big circle here. Here's g of x. As this rotates around, we'd get this little circle. And then what we really want is we want the in-between part. So we want to take the big circle minus the little circle, because all the rest of that's whole. So the washer method is equivalent to applying the disk method twice, once for the overall solid and another to compute the volume of the hollowed out cavity within the overall solid. The cavity volume is then subtracted from the volume that enfolds it to obtain the volume of solid of revolution. So the volume of a washer, there's our washer there, is going to be pi times the integral from A to B, r squared, where r is the outer radius, it's our upper function or outer function, and then minus little r x squared, where that's the inner radius, it's the lower function. So if we're integrating with respect to x, it's going to be upper function minus lower function. If we're integrating with respect to y, it's going to be function to the right minus function to the left.
So it's the same thing, you just change the formula for the radius or whatever, the shape. The area
Yes.
shape. Okay.
Yeah. All right, so the volume of a solid generated by a region between f of x and g of x bounded by vertical lines A and B revolved about the x-axis or a horizontal line is going to be pi times the integral from A to B. The absolute value of f of x squared minus g of x squared. Not to really worry about too much about the absolute value. I haven't seen that be really a problem. And if we're, for the most part, it's generally not a problem. I guess if we have negative numbers, if we're rotating on the other side of the x-axis, maybe, but it will be positive. Right? We won't have negative volume. That won't make any sense. If we're rotating around a vertical line, rotating on the y-axis, we have pi times the integral from c to d. Now it's going to be f of y squared minus g of y squared dy. This one is going to be upper minus lower function. And this is right minus left. All right, so there are our formulas, right? And so let's take a look at these. So here is the disk method. So the disk method, there's no hole in it. So it's a solid, right? So we just take the distance from our line of revolving around to the function. That's going to be our radius. Our cross section is a circle, so it's just pi r squared. If our function has a hole in it, then we have our object has a hole in it. Then we have a washer. So notice there's a hole in our cross section. So we need to subtract out the hole. So we're going to take the outer function minus the inner function. Squared, of course, because it's area of a circle. All right, so using the Wasser method to find the solid generated by revolving the region by y equals x cubed and y equals x in the first quadrant about the x-axis. Draw yourself a picture, okay? So I drew that lovely, lovely picture there. We've got the line y equals x is on top there. And below that we have the line this curve y equals x cubed. All right, so there they are. The red one is the functions there. And then I'm just showing as it revolves around, we have a mirror image from rotating. Right? And so we have this filled in portion here that I marked in yellow. And then we have that hole right there in the blue. Right? So to find the points of intersection, you're just going to set your function equal to one another. Right? We are going to be in the, notice it says first quadrant. So any value that when we solve is not in the first quadrant, we'll eliminate. So we have x equals x cubed, subtract x from both sides. You've got x cubed minus x, factor out an x. You got x times x squared minus 1. Of course, x squared minus 1 factors into x plus 1 and x minus 1. So you've got three solutions there. You've got 0, you've got negative 1, and you've got 1. Can't use negative 1 because that's not in the first quadrant. All right, so now you determine your outer and inner radii. All right, so the outer function here is the upper one is the x squared, and the inner function is our x cubed. So the volume is going to be pi, evaluated on the interval of 0 to 1, and then our outer radius is x squared. The inner radius is x, is x, but then be x squared, is x cubed, so we square it because we're finding the area of a circle. So it's upper function squared minus lower function squared. And then all you got to do now is integrate, square, integrate, and evaluate. All right, so if I could square this, it would just be the volume equals pi from 0 to 1. We'd have x squared minus x to the 6th dx. All right, so we integrate that. Oh, I have it written down there too. It's going to have pi, and it'll be x cubed divided by 3 minus x to the 7th divided by 7, evaluated from 0 to 1. So the 0 won't matter here, but the 1 will. So now I have 1 cubed is be 1, so divided by 3 would be 1/3, and then 1 to the 7th is still 1. So we have 1/3 minus 1/7 times pi, which is 4 pi 21st. So that would be the volume of the solid. Okay, so these solids are not solid.
The solid that has a hole in it.
This is the solid that has a hole in it.
So you get,
So you get the volume from the y equals x
Mm-hmm.
and the one from the bottom?
No, it's these two functions here.
Okay.
Okay, so the revolving, okay, well, people in the, and only the people here can see me cover up the shape, but I'm answering Lanji's question, and so the functions in red are actually those are the two functions graphed. This is their mirror image because they're revolving around. So if I just graph the lines, it's just that area there, but that area is being rotated, so that's what creates this part here. So I just drew in the rest of the figure so you can kind of see it, which is a good idea actually to get a sense of it. Then you can see where your outer and your inner is. Right? So the outer is going between the outsides of the function, and the inner is between the two functions. So if I didn't have that inside function there, and I just rotated the line around, we'd have a cone.
Yeah.
With no hole.
This is easy.
So, wish I'd written a little smaller here. All right, here we use the washer method to find the volume of the solid generated by revolving the region, in this example here, about the line y equals 2. So now we're going around a different line here. So the function that we're revolving is not written down here. Let's try to move this up a little bit. Make that clear. Oops. I don't know. My be careful here is, there we go. All right, so we're revolving the line y equals x cubed. That's the function. And we're revolving it around the line y equals 2. All right, so there we have that graphed. Okay, so I have a little note there. Be careful, upper isn't always outer, because 2 minus x cubed, the axis of revolution, is above the function. So here is the function. There's the line of revolution here. So the outer function is going to be our outer function is the 2, because that's the line above it. So you got to be careful on this one. So you got, kind of point this out for everybody. So it's three-dimensional there just because we've drawn in the mirror image. Ooh, I can't stretch any further.
Oh.
Yeah. All right. So here's the actual function is down here. So it's y equals x, and then we have the x cubed here. And we're revolving around this line y equals 2. So since the line's above here, the outer one is not just x cubed, but the outer one is 2 minus x cubed, because we're revolving around this line. So you got to take that into account if you revolve around something besides the x-axis. So here, if we were going around the x-axis and not y equals 2, y equals x is the outer function. Because we're going around the line above there, y equals 2, instead it's y equals x cubed is now the outer function. This is the same problem, same function, but revolving around a different line. And notice we create something different now. Now we're creating a bowl. So 2 minus x cubed is our outer function. Our inner function is 2 minus x. All right, so now we take the outer minus the inner. All right, so 2 minus x cubed is the outer function. And then the 2 minus x squared is the inner function. So that inner function there is creating our whole, right? So this one creates the whole. All right, so now we just square and then evaluate. And then, I don't remember if it said to solve between 2 and 1 on this problem. I think it did on the other page because it's the same problem, 0 to 1. So it's the exact same problem except revolving around a different line. All right, so we've got 4, we square the 2 minus x cubed, and we get 4 minus 4x cubed plus x to the 6. And then we, where does this one line go?
On the bottom, as it continues going later on, right?
Is it? I don't know.
Yeah, I'm pretty sure. If you
Who
could
knows where it goes? Here, we'll just start anew. We'll just start anew and we'll write smaller this time. How far that goes down. And you can write a little bit smaller. Boop. You guys will help me with the math. All right, so here we'll integrate and evaluate this. All right, so we've got the 4 minus 4x cubed plus x to the 6, and then minus the 4 minus 4x plus x squared dx. So now we'll integrate, and as I integrate, I'm gonna distribute the negative. So volume is pi, and we've got, this would be now 4x minus 4x to the 4th divided by 4 plus x to the 7th divided by 7, and then minus 4x, and this would be minus a negative, so that's going to be a plus. So that's going to be plus 4x squared divided by 2, and then minus x cubed divided by 3. And we get a couple like terms, and actually they're going to cancel each other out. Oh, and that's from 0 to 1. So our volume is pi times the 4x and the negative 4x are going to cancel. Nothing else cancels, but we can reduce here. So we have negative x to the 4th plus x to the 7th divided by 7 plus 2x squared, and then minus x cubed divided by 3. And that's from 1 to 0. So now we'll just do the plug-in. So our volume is pi, and we've got negative 1 to the 4th, the negative's not in the parentheses, plus 1 to the 7th divided by 7, plus 2 times 1 squared, minus 1 cubed divided by 1, and then, of course, minus 0. Because if I plug in, I'm just going to have a bunch of zeros. Make sure, though, that when you have a 0, that's really 0. This is really 0. Sometimes students do that with cosine. They have a minus 0, and they don't plug in 0 to cosine or e to the x, and then it makes a difference. This one doesn't make a difference. All right, so that's going to give us our volume is going to be pi times, we've got negative 1 plus 1/7 plus 2 minus 1/3. And so now all we got to do is combine our terms. So our volume is pi. So negative, that's going to be 1, and then plus 1/7, and that would be 3/21. This would be 21/21 minus 7/21. So that's going to be 17/21. So our answer, our volume is 17/24 pi. There it is. So really, once you know how to set these up, they're not really difficult. Here we even revolved around a line, not the x and y axis, and it still wasn't too difficult. Okay, just make sure you use that 2. So notice that my line, because I'm revolving around 2, it's the distance to the line, so it's not an x cubed, it's a 2 minus x cubed, and it's not an x, it's a 2 minus x.
So where'd the pi go when it was 21/21, when you turned them all into 21s?
Oh, I was just adding those numbers up. Yeah, so I just went to simplify that up there because I had a little bit of space. Yeah. So this here is just me simplifying that. And I guess I'll stop the podcast with this problem, and then we'll pick up on the next problem.